Hi. In earlier lecture, we have mentioned the Feynman-Cat approach several times. So what exactly is the Feynman-Cat approach? So essentially what Feynman-Cat approach is that they claim, well, actually, not just claim, they showed and they demonstrated that the solution of certain PDEs, PDEs of certain forms, can be arrived at through integration under suitable probability density functions. So the fundamental PDE that we have is a type of PDE that we can utilize that approach. So for the rest of the lecture, we're basically going to see integration under probability density function. So, and that is equivalent to, the result of that is equivalent to solving that PDE. So you can solve that PDE by doing an integration over probability density function. And that integration will lead us to show that this particular condition is true, okay? So now what is this basically? So we were saying that an expectation of this function here takes that particular form. So the expected value or the expectation of this particular function, max function here, is really an integral where we integrate from k to infinity of x minus k with the probability density function gx dx. Now, gx is the PDF probability density function of x. Now, if x follows a log normal distribution, so if x is the log normal process, then the log normal distribution log x, the log x will have a mean and also a variance, right? So now, what is the mean and variance of log x? It's much easier to integrate over a normal distribution there, normal probability density function. So that's the approach we're gonna take. And we know log x has a normal distribution if x is log normally distributed. And log x has a mean and a variance, where the mean, if you just look at the distribution there, the mean is log expected x. So this is the mean of the log x. This is the mean of x. Okay, so the mean of log x is the log of mean of x minus the variance of log x squared. Sorry, the variance of log x divided by 2, or the square of the standard deviation divided by 2. Now, we have a bean here, but we want to further simplify our task. So we want to integrate over a standard normal distribution. So let's do a change of variable first. We're going to see several change of variables throughout this derivation here. So the first change of variable is we define a variable q. And q is really log x minus the mean divided by w. So then q is distributed standard normal. Okay, so if q is log x minus m divided by w, then x is then e to the power qw plus m. Okay, so we have expression for each other. Now the PDF for Q then is this very simple standard normal probability density function. Now our task is to integrate or to calculate expected value of this max function here. Now, given that approach, so we're integrating basically x, which is e to the power of qw plus m, so x equal to that, minus k, and under this distribution of hq dq. Now, since I've changed the variable here, the integration we will not start with k here. We have to start with log k minus m divided by w. Okay, so now, okay, this is just an equivalent way of expressing this expectation value. But this equivalent way of expressing that makes it the derivation much easier. So you look at the integral here, and this is one minus the other. So they're linear, so you can break them into two parts. So I've color coded here. So the part related to e to the power of qw plus m, I've color coded blue, and the part related to k, I've color coded to yellow. Okay, so we can break this into two components, and then we tackle them one by one. So we will first look at this particular integral. Okay, so now in the integram here, right, we have e to the power of qw plus m, and times this density function hq. And so we just write it out. hq is this standard normal distribution density function here. And once you have that, there's a q here, there's a q here, so you can actually bring them together. Then you will have this particular expression here. Now, once you have done this, you can, this part here, 2m plus w squared, is not really related to q. So you can take them out. So you have this constant factor here, and then multiply by something that's blue. So anything inside here. Now, if you look at this particular thing, this is actually, again, a standard normal probability density function with q minus w as the variable. Right? You can treat it that way. So what we're going to do is that we basically we can pull this out so that the blue part becomes a constant, which we figure out here, and multiply by this standard normal, the expectation under standard normal distribution for a new variable, essentially q minus w. Now, there's a few things that we can use. Number one is if we switch the order, the places how we integrate. So here, if we integrate from minus infinity to x, and then we know basically this is the definition. Then it's the nx, and nx is actually defined this way. Now, if we switch that from, instead we integrate from x to positive infinity, then is basically the other side of this area under the curve. And that is basically 1 minus nx. So we have this condition that we can use, which means that 1 minus nx is really equal to n minus x. Okay. And the other part here, we talked about we have this Q minus W, we have dW here. So if we call this Q minus W a new variable, so the second time that we do a change of variable here, let's say we define a new variable beta, which is equal to Q minus W here. And when we do this integration from x to infinity becomes an integration from x minus W, which is this part, to infinity. And you will see that d beta is really just dq, so there's nothing changed here. And beta is equal to q minus w, that's why you have beta here. Okay, so your new name for q minus w is beta. And if you put it in this form, then based on the definition here, it's really just n function with the argument of minus log k plus m divided by w plus w. Okay, because you are integrating, then you integrate from x minus w is really this, so you have this part here. To see this is the case, we have this log k minus m divided by w is really this x here. So x minus w is log k minus m divided by w minus w. Okay, and minus what we have here is then is minus x. So if x minus w, the new x is this thing here. Or in this case, we have changed the variable to beta. So beta is the new x. So beta is this, minus beta is this part here. If you rearrange minus of this thing, it's just what we have in the bracket here. Okay, then, and the reason we have this is because we're integrating from a number to infinity rather from minus infinity to a particular number x here. So we're actually from a number x, which is in this case, we integrate from beta to infinity. So from beta to infinity is n minus beta. And this is beta, this is minus beta. So we're getting n minus beta here. Now, we know m has this expression here on earlier slides. Then we just substitute in m. Whenever we see an m here, you put in an m here, you rearrange, then you have this particular form here. This basically is ND1. So ND1 we've written here. That's for the ND1 here. This is the D1 here. So D1 is equal to what's in the bracket here. So we have shown that the what's in the we have this part here, and anything in the integral here is basically ND1. Now we have this part that we need to figure out, and also this yellow part as well. So for the yellow part, it's actually very simple because if we're integrating a particular thing, right? You're integrating the this is the probability density function, standard normal probability density function. If we integrate over that, this by definition, this is n of this thing here, nx. So from x to something, actually, sorry, m minus x. So what's in the integral here, what's in the bracket here is minus of this log k minus m divided by w. Okay, so we have an n minus x here. Now, again, we know m is this log expected x minus w squared divided by 2. So we substitute in the m. So we have this part here. And essentially, then we have n d2. So this part is really d2, which is, if you look at it, is d1 minus w, because the d1 has a plus sign here, plus sigma square plus w squared divided by 2, and we have here is minus w squared divided by 2. So this part is d2. So then what is this? Again, you can put in this m, and then if m is equal to this, then you basically have e to the power of log ex and times nd1 minus k times nd2. Because you have m plus this thing here, and m has one that's minus w squared divided by 2. So this part and this part canceled out. So you're left with e to the power of log en. And basically that is just en, the expected value of x, then times nd1 minus k times nd2. So finally, we have shown that the expected value of max x minus k, or 0, is then ex nd1 minus k nd2. And I want to remind you that this condition is only true when x is log normally distributed. Okay, so it's not true if x follows a different process. But if x is following a log normal process, then we have this very nice and simple form here that we can utilize. So you see a lot of the time when they try to derive closed form solutions to price derivative products, a lot of the time they have to rely on the underlying variable following the log normal process. And if at the log normal process following by the underlying variable, we can then utilize this particular condition, and that will allow us to derive the closed form solution for price.